So now let's look at parametric methods comparing two, what do you call this? Two sets of data or two parameters, so to speak. So we now have the Wilcoxon sign rank test for comparing paired or dependent samples. We're supposed to be tested. So the Wilcoxon sign rank test can also be used to compare paired or dependent samples. Again, remember when we say we have dependent samples, this really means that there's only one sample. So for example, your sample, so for example, you have your sample of 1, 2, 3, 4, and so on, but you have two data sets from that one specific sample, and these two are what we call our dependent samples. So this is the non-parametric counterpart of the paired samples t-test, or the dependent samples test. So let's have this specific example. Two computer software packages are being considered for use in the inventory control department of a small manufacturing firm. The firm has selected 12 different computing tasks that are typical of the kinds of jobs such as a package would have to perform, then recorded the number of seconds each package required to complete each task. The results are shown below here. At 0.010 level, can we conclude that the median difference for the task populations might be 0? So if the difference is 0, they're asking if these two are equal. So let's now go to Excel to perform this test with XLSTAT. Alright, so we have our data here, and going back, we are asked on whether the median difference be 0. So we just like what we did, if we're working with XLSTAT, let's already declare our HO and HA. So with that, let's have this one. Let's go on button here. So first we say, so we say that our HO would be our HO would be that the median time for package X would be equal for the median package, or for the median of package Y, because the difference is 0. So although we can write it this way, by transposition, that will be equal, and that's what we've been using ever since. So the alternative is that the median of package X is not equal to the median of package Y. So there you go. So now let's go use XLSTAT for this. For non-parametric test, we now go to comparison of two samples. So there you go. First, we go to one column per sample. So sample 1 is this. We select package X. And then sample 2 is package Y. What we need is Wilcoxon sign rank test. So we select that. And we select, and automatically you can see we select paired samples. So, if you, a while ago, if you select this, then you select that, it's kind of automatic. So we have to go to, I'm going to have it also in a different sheet. Then here, on the options, we have here sample 1 minus sample 2 is not equal. And that would be our alternative hypothesis. As you can see here, it has different alternative hypotheses, and what we select is this. Because we want to know whether they're equal, the medians are equal or not, we'll just have this one. And the hypothesized difference is 0. According to the problem, at 0.10 level of significance here, so we're going to use 10% level of significance. It's 10 here, exact value, then the rest is okay. Alright, so there you go, and then we click OK. We click continue. So we have again our summary statistics here if you need them. And then we now have our Wilcoxon here down below. So we have our sign test here. What we need is the Wilcoxon sign test here. Here. So here you go. So this is now our steps 2 and 3. And for step 4, the p-value of 0.029 compared to 0.10, obviously this is lower. Therefore, we reject our HO. So the conclusion, is that there is sufficient evidence to reject HO. Thus, the median of package X is not the same as the median of package Y. So that's how we use Wilcoxon sign rank test. So the other problem that was previewed a while ago here, I'm going to leave that on your own so that you'll be able to practice. Now, Wilcoxon sign rank is used to compare paired or dependent samples. For independent samples, we use the Wilcoxon rank sum test, also known as the Mann-Whitney U-test. So, the reason why we interchange because Wilcoxon was the first statistician who computed this test, and then two other statisticians, namely Mann and Whitney, improved this test. That's why they share the same name. So the Mann-Whitney U-test, also known as the Wilcoxon rank sum test, compares two independent samples and is the non-parametric sample, a counterpart, of the two sample t-test. The test assumes that the data are at least of the ordinal scale, so it's ordinal, interval, or ratio, and the samples are independent and randomly selected. And the populations would have exactly the same shape, not necessarily normal, but at least the same shape. When doubt exists as to whether data meet the requirements of the interval and measurement, the interval or ratio scale of measurement, or if it cannot assume that the populations are normal with equal variances, the Mann-Whitney U-test should be used. So let's have a specific example. In evaluating the flexibility of rubber tie-down lines, an inspector selects a random sample of straps and counts the number of 360-degree twists each will withstand before breaking. So, for the 7 lines from one production lot, these are the number of turns. For 10 lines in the second production lot, here are the number of turns. At 0.05 level, can it be concluded that the two productions have the same median flexibility? So let's now go to Excel for this. So let's just show an example with just production lot right here. Okay, so let's just show like a full process. Let's assume we just got this data and we don't know whether to use t-test or Mann-Whitney. So the thing that you should do is check the normality of the two. So we go to distribution fitting and check whether these two will not stay the same here. Here, check whether they are normally distributed or not. So let's check, let's have this one here. And then we have to estimate. We have to do this 2 times because we have 2 data sets. There. So I'm going to click OK to check for that one, then continue. It's supposed to be near here. One. Anyway. So there you go. You have your 7, and it shows that the 7, the production lot 1, are more or less normally distributed. So for the first one, it follows. So let's check the second one. So let's do again distribution fitting. This time for the second one, and we do the same thing. So for this one here, so it looks like based from our Kolmogorov-Smirnov, the two are actually normally distributed. So more or less, we can also apply t-test here. But since we want to show our Mann-Whitney, that's what we're going to do. So, since we're doing non-parametric, let's first declare our HO and HA. So, according to the problem, the two lots have the same median flexibility. So, that would be our HO. That the median of production lot 1 is the same as the median of production lot 2. HA is that they're not equal. So that's a two-tailed test. And with that, let's now do our test here. So we go to here. Comparison of two samples. Then we just go into F1. We select production lot as home first. Then for the second, oops, we select this one here. There you go. And what we're going to do is, there you go, the Mann-Whitney test. There you go, options. The sample is still the same. Let's just take our alpha, it's 0.05. We need to change this to 5%. Then since this is equality, it's still the same alternative hypothesis. It's not one. So with that, good. Okay. Then continue. Oops, sorry. There you go. So we have here our summary statistics if you would need them. So now we have our steps 2 and 3. So now for step 4, the p-value of 0.075 as we compare it to 0.05 is bigger. Or let's just say it's not less than. So not less than 0.05. Hence, we have failed to reject our HO. So we conclude there is no sufficient evidence to reject HO. Thus, the median of the first production lot is just the same as the median of the second production lot. Go. So I'm going to leave number 2 as an exercise for you to do, and that's some of the non-parametric tests that we do with 2 samples: the Wilcoxon sign rank for dependent samples and the Mann-Whitney U for the independent samples.